Hello, everyone. Come on in. Come on in. Anybody have any questions before we get started? You'd think you could smear a whole jar of mayonnaise on your glasses and see through it just fine, but evidently that's not the case. Okay, so hi everybody. Long time no see. Hope everybody are getting ready to do pretty well on their test one anyways. That's due tomorrow night at 11:59 p.m. And then the next one's going to be due shortly thereafter. I think it's like the 13th, maybe. Anyways, I hope you are keeping up with that. Anybody have any questions on any particular problems you've ran into, either in homework or practice tests or whatever? Otherwise, we'll get cracking. All right, got another person coming in. There's only 10 of you in here right now. So actually, we got up to 11. Woo-hoo! So no questions, questiones, quid, quiz, Quomodo, any of that. All right, well, I guess I'll get started. So the last time we talked, we had worked a couple capacitor related problems. For instance, I actually didn't do the problem where you connect a capacitor and actually it was connecting two capacitors in parallel with a certain voltage, and then you charge them up and then you disconnect them from the from the battery, and then you disconnect them from each other and flip them and then put them back together. That's a neat problem. I think what I'll do is I think I'm going to make that video and put it online as a little standalone. I might even make it in two parts, because the first thing I need to you guys understand is what happens when you actually attach a capacitor via a wire, of course, a capacitor to a battery. I want that as an intro, but I also want that as an intro to connecting capacitors to batteries and solving capacitor problems, but also as an intro to a differential equation that we'll introduce later that we solve and tells us exactly how the charge, the voltage, and the current behave over time in first connecting a battery to a capacitor. So I'll probably do that instead. I'll just go ahead on with a couple other problems. So tonight I planned on working for you a old style antenna cable that I remember back when I was a kid. My grandparents had, and I never remember us having one, so it might have been a little bit older than my technology at the time. But the main thing was it was a neat little flat wire that they ran to an antenna, and it was flat, and then it had like a clear vinyl or plastic type material. It almost looked like those skate or stingray eggs that you see on the beach, where they're like a little pod and they got a little black thing. They're black for starters, and it's like looks like a little purse thing, but actually, heck, it looks more like a mask for COVID, because it's got a square like this, and then it's got a string and a string, but it's all black and it's a little fat in the middle. But anyways, that's what this stuff looks like. It's just really thin, flat in the middle. It's got two little pieces of wire that you can actually see through the outsides. That was the cable at the time. So we're going to calculate the capacitance of that. And then I'm going to calculate the capacitance of two isolated concentric conducting shells, spherical shells specifically. And then from there, I'm going to see what else I can do in terms of getting you up to speed on teaching you about the molecular description of capacitors and stuff like that. So does anyone have any questions before I get started on all of that fancy rigmarole and gobbledygook and whatnot? Anyone? Okay, it looks like we're pretty question free, either that or everybody's typewriter, everybody's keyboard, and everybody's microphones are not working. So I'm assuming that that is not the scenario. So I will press on with my applications. So my intent is to first off share screens with you guys. And what I'm going to do is share the screen of my iPad, specifically using GoodNotes, I think it is, with a blatant advertisement from my page right across this top. Just started doing that recently. I started thinking, I bet you my students probably think I'm like just trying to advertise or something. Not really that. I just wanted y'all to see it, so maybe y'all would remember it. And hopefully y'all will subscribe at least long enough for the semester to end. So the first thing we're going to do is we're going to again go over an instance of starting from Gauss's law, using Gauss's law, or in some sense Coulomb's law you could use as well, to compute the electric field at some point in space. Then we're going to take the definition of voltage and calculate the voltage difference from one particular charged item in space to another oppositely charged item in space. And then thirdly, we're going to take the definition of capacitance, which is a charge held divided by the voltage across, to calculate the total capacitance. So that's what we're going to do. And I'm going to first do it with two concentric spheres. So let me start off by making a coordinate system, and my coordinate system is going to be an XYZ coordinate system, of course, but it's also going to be where my sphere is going to exist, and I'm probably going to go a little bit into spherical coordinates just for a little picture of what spherical coordinates are. Okay, so let me do this for just a second. Bear with me. I might even just erase everything when we're done as far as the spherical coordinate stuff goes. So if you have at a particular point on the x-axis and another particular point on, say, the y-axis, okay, then that clearly gives you enough information to find a point in two-dimensional space. Be right there. Now, if you also, obviously, in addition to that, have a position along the z-axis, then that's got enough to give you a position in three-dimensional space. So it turns out this position right here is z, and that coordinate right there is x comma y comma z, and that's our normal Cartesian coordinate system. But it turns out that it's really, really convenient to consider some other coordinates. For instance, if we take from the positive x-axis and lying in the xy plane and measure that angle right there, and actually I probably should write it the other way, then that angle will be called the azimuthal angle theta. Okay, that's the same theta that you use in polar coordinates, and it's the same theta that you're using in cylindrical coordinates, and it's the same theta that we'll use in spherical coordinates. But there's another theta, there's another angle as well. So that's the angle theta, and you can see that would only isolate me down to one point on some infinite line. As you can tell, there's an infinity of distances away from the origin, and then that's just in the xy plane, and all of those make a line. But if you include the z axis, then all the planes that go through that one particular line, which are not only the vertical ones, they're everything but the horizontal ones, then you have a whole plane that's infinitely large, and that's why one coordinate is just not enough to define a point in space. Now, if you were dealing with just two dimensions, as I said, then there also would be this distance r right here. And in polar coordinates, you'd call that point r theta. And that would be just fine. But there's a couple different ways you can go from here. You can go to cylindrical coordinates, which means you would just add to that r theta z, and that's cylindrical coordinates. Okay, and in fact, you would define the r hat vector as a little vector that continues along this line in the xy plane, has a unit length, and points that way. Then you'd say the theta vector is in fact also in the xy plane and is 90 degrees ahead of it and looks like that. And then, of course, the k vector is 1 unit long, pointing in the positive z direction. So you'd actually have the complete cylindrical coordinate with its triad of actual unit vectors. Now, in the spherical coordinate system, we switch up a little bit. So I'm going to change my color completely to say green. And instead of r being there, we go from the origin to there, and that is r. But it also agrees that this is theta. So this point can also be called r theta and then phi, where this is called the azimuthal angle. And this one's called the polar angle. And what that is that angle goes down from the z-axis this way, and that's the angle phi. Okay, so there's your two coordinate systems that we've been dealing with. I just wanted you to have some idea of what they look like. Obviously, in this one, you get a r hat that has a z component. Obviously, it continues along that radial line from the origin to whatever point in space you are, and it points away from the origin, so you know that's where that is. The theta hat is in fact the exact same theta hat vector that we had in cylindrical, so it actually exists in the xy plane, but can be moved at any altitude as well. So this one would actually be hard to see in this angle, and that would be the theta hat. But then the phi hat would be perpendicular to the r hat and points in the direction of increasing phi. So it would look like that. So that's actually what the unit vectors look like in the system. Again, this is not the best particular orientation for the to demonstrate the r theta and phi hat. At least the theta hat, it's kind of not very good. But anyways, that's what the coordinate systems we've been using look like. And I don't need you to be familiar with how to convert them. I think you can see from here that the r in cylindrical is just equal to, in magnitude, the square root of x squared plus y squared, whereas the r in Cartesian is the square root of r squared plus y squared plus z squared. You can see that r times cosine theta is x. You can see that r times sine theta is y, and that's the truth in cylindrical coordinates. But you'd actually have to take r sine phi, that polar angle, r sine phi times cosine theta to get the x hat. If you're dealing with with spherical r hat or r vector. And then if you were dealing with r in spherical, you would also have to take r sine phi times sine theta to get the y coordinate. So hopefully that between that and all that description I just gave you, that's enough to discern all of them. Now what I'm going to do is erase all that, and it'd just be easier to erase all that and then draw a new coordinate system and draw the concentric spheres that I was mentioning. So I am now going to go back to black to draw my coordinate system. And I'm going to let the system cheat a little bit for me by making my lines really straight. And like that. Okay, now I'm going to turn off the cheating system and call that X, call that Y, call that Z. And now I'm going to turn on the cheating system again because I need to draw the actual object. And I think I'll use green again because I really like green. So what we're going to have is a inner sphere. You can think of it as a spherical shell. It could be a solid sphere. The main thing is all the charge is going to be on the outside edge. So I'm going to draw it centered on the origin. Oops. And evidently the thing that made that pretty also noticed that I picked up my pen for just a split second. So it stopped making my circle. And that time it was not on make my stuff pretty. That time it was good. Okay, so let's call this a radius RA, and that's lowercase r, lowercase a. All right. Now, what I'm saying is that's going to have an amount of charge plus Q on it, and I'll draw that in the diagram form in a little bit. But right now, I think we're good with this. So now what I want to do is draw the other concentric sphere. So it goes around like this. Okay, and that one has a radius that goes from here to here, and of course is R sub B. Now inside of that has a negative charge Q. So what I'm going to do is I'm going to say right here has a charge plus Q, and I'll indicate that with a bunch of little plus symbols. Well, I say a bunch. Let's just say a few. Okay. And then on the inside of here, I'm going to have a charge of negative Q. And I'm going to indicate that with a negative sign, 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 like that. Okay. And what I would like to know is what is the capacitance of this? So the real question here is C, which is defined as Q over V, is equal to question mark. Okay. So I'm going to start off from Gauss's law and complete this. This is what I was telling you, sort of a capstone problem in the sense that it actually encompasses so many different things that it's one question that can sort of do the work of 3 or 4 chapters. So my solution I'm going to write in blue. And I'm going to start it right here. I'm kind of a little bit OCD, and I'm bothered that that doesn't look very spherical. So now I am, in fact, going to try to make these spheres look a little bit more spherical, which I think you can see now that that's a little bit more certainly spherical as opposed to circular. And if I want to add just one more bit right here, I think that would look a little more spherical. Okay, sorry about that. Just a pet peeve of mine. All right, so what I want to do is first I want to apply Gauss's law. Gauss's law says the closed integral of E. Well, let me draw that whole E over again. Dotted with dA, in other words, the net flux through a closed surface is equal to the charge enclosed divided by epsilon naught. And what I am going to do is I'm going to take the symmetry that I see in this problem, specifically the fact that the charge of these two conductors exists basically on the outer surface in the case of the sphere inside, and on the inner surface in the case of the sphere on the outside. That's where the charge exists, and it's uniformly distributed over it. So in fact, it's a spherically symmetric charge distribution. And because of that, I want to go with a hypothesis that E, the vector, is only going to depend on the spherical coordinate R in terms of its magnitude. In other words, how far away a particular point is in space from the origin. And then it's going to point in the spherical coordinate R hat direction. In other words, it's always going to point radially outward. That is my hypothesis. And that is also a hypothesis that allows me to come up with a Gaussian surface. So the deal is when you're using Gauss's law as we are here, which is in such a way that we try to extract the magnitude of the actual electric field from the integrand of the integral on the left, we need to have certain symmetries in order to do that. I mean, Gauss's law, as my friend Casey used to say, is Gauss's law. It's not Gauss's helpful hint that sometimes works. And because of that, we know that it always is true, but to try to extricate that E out of the closed integral E dot dA, we need certain symmetries. And the symmetries are, it's got to be basically infinitely large and flat. It's got to be infinitely long and cylindrical, or it's got to be circular. So if we do that, then we can get neat things. So now that I've made this hypothesis that the spherical, I called it circular a second ago, I should have really said spherical, that the spherical charge distribution is going to create a spherically symmetric electric field. And spherically symmetric means that for any particular radius from a pre-chosen center, then the magnitude of that electric field is going to be a constant. So that's why I said E is a function of R only, and I didn't use an R vector as the argument of E. I just used the plane R. And it means since the equipotential lines have to be, or planes, if you will, have to be perpendicular to the electric field lines, then you know the R hat is the direction. So because of that, we're going to choose a Gaussian surface that's also a concentric sphere. And by doing so, the left-hand side will just become an electric field for a very specific radius, namely the radius of the Gaussian surface in this spherical case, times the integral of a surface area, which in this case will be the surface area of a sphere. Now, in general, that's what you're always supposed to do with Gauss's law. So keep that in mind. In Gauss's law, when you're trying to use the integral form, as we are here, to solve for the electric field, you need one of those symmetries, basically a really large flat plane, or a really long straight wire, or a really long straight cylinder, or finally a spherical situation. But in all of those cases, you can then define a Gaussian surface so that the electric field times the area, a constant electric field that is, times a very specific area or portion of the surface area is what you get on the left-hand side. Now you might get E times A plus E times A, or you might just get E times A, where you actually specifically have to write out what the A is. Like for a sphere, the A is 4 power squared if you talk about the surface area of the sphere. If it's the surface area of, say, the soup label of a soup can, then it's 2 power R times L, and then that'll be times E. But that's the main thing. So the left-hand side is always supposed to come out to be electric field times some area or a sum of them. And the only way you do that is everywhere on the Gaussian surface, the electric field has to either be a constant or it has to be perpendicular to the dA vector on that particular part. So now I'm going to draw my Gaussian surface, and I appreciate your time in allowing me to explain all that again. But let me try to draw a spherical Gaussian surface. I'm using the cheater function again in hopes that it will make it look better. And it looks like it did. It did a good job. I still can't stand the fact that that doesn't look very round or spherical. Whoa, 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 whoa. What's going on here? Okay. So I don't like that it doesn't look that spherical, so I'm putting this on here. Okay, and I think you can now see that it's definitely more spherical than it is circular. Okay, now that's going to have a radius R, and this drawing's getting busy now. That's going to have a radius R, and as you can see, that R is in fact larger than RA, but smaller than RB, and it's drawn right here. So yes, that drawing got a little messy, got a little that sort of thing, but I think given the order in which we drew it and the long time lags between, y'all should be able to make it out. That being said, that means that everywhere on this Gaussian surface, the dA, which actually, if you knew your spherical coordinates, you could actually figure out what the dA is. But in this case, it's not going to matter too much. We're just going to integrate dA to get A, and then we're going to write out A as the surface area of the sphere. So I'm just going to write dA and the fact that it points in the R hat direction, which means it's going to be parallel to E. Remember, I told you either the electric field needs to be a constant on the Gaussian surface, or any place that it's not, it's got to be perpendicular to the dA vector on that particular part of the Gaussian surface. Well, it turns out if your electric field is constant on a surface, then the dA vector for that surface is essentially by definition automatically parallel to the E vector at that point. So that's what we're getting. Now, the way I do this is I do my left-hand side. So here goes left-hand side of Gauss's law. And that is the closed integral of E dot dA. In this case, it's going to become the integral of E of R. And that R, as I said earlier, is bigger than R sub A and smaller than R sub B. That E of R is multiplied by R hat because that gives its direction. And then there's a dot product of the dA vector, which has a magnitude dA, which is literally also the length of the vector dA. So I'm going to write dA, and it happens to point in the R hat direction. And I'm going to write GS here just to remind you that you're integrating over the entire Gaussian surface, which in this case was a red sphere. So let me also do this. This is your Gaussian surface. Now, the main thing is your surface always has to be closed, or Gauss's law doesn't work at all, for that matter. All right, so now that I've got that, what we can see is, okay, really we are evaluating the electric field because this integral is technically a surface integral. That means the integrand has to be evaluated on the surface. Well, the surface has a cylindrical coordinate R equal to exactly R. Therefore, E of R is a constant, And the dot product turns out to be a linear operator. So I'll take a couple steps actually. First off, I've already explained to you that E of R is a constant, but I'll leave it there for right now. And then I'm going to pull the dA through the dot product just to show you that the dot product is what we call linear, which means you can pull vectors through them. I mean, pull magnitudes through them and just leave the r hat dot r hat. Or if you had, a scalar plus a scalar times r hat, then you can pull the sum of the scalars as well. But the main thing is we're now left with that. This happens to be 1 times 1 times the cosine of 0. And that, of course, is 1. To me, this looks like a intoxicated owl. But anyways, that's just a fun thing I like to do. Now, or I like to say. Now, because the electric field has been evaluated at a very specific radius r, this electric field is really just a constant E of r for that point. And this is just an integral dA over the Gaussian surface, which, as we said, was in fact a sphere of radius r. So I'll say of radius RA less than R less than RB. So radius R. Okay. So we know that the formula for the surface area of a sphere of radius r is 4 pi r squared. So the left-hand side just becomes E of r times 4 pi r squared, and the left-hand side is done. Now, because we were smart enough to write down exactly what the charges were, and they gave it to us in such a way that it was easy to deal with, we can easily evaluate the right-hand side of Gauss's law just by saying Q enclosed over epsilon naught is the right-hand side. In this case, that just becomes Q over epsilon naught. I can now let left-hand side equal right-hand side. I'm looking up. I still don't see any hands raised or anything. That makes me feel like I haven't completely lost you, but I didn't put up the chat, so it's up now. So the left-hand side equals the right-hand side. That gives us E of R times 4 pi r squared is equal to Q over epsilon naught. Now we can easily solve for E of R, and then we can go back to our hypothesis and use that E of R to say what our actual electric field is. And now I'm going to do that. I'm going to say E, the vector field, is equal to Q over 4 pi epsilon naught r squared times r hat. And that is, in fact, the electric field for RA less than R less than RB. Okay, and that's actually where we needed it. So that was step 1. Step 2, as I had mentioned to you before, step 1 is to find the electric field. Hopefully you can do it with Gauss's law because that's easier than Coulomb's law. Otherwise, you have to do it with Coulomb's law. Step 2 is using the definition of voltage to calculate the voltage difference between the two parts of the charged object. In this case, one being positive charge, positive Q, and the other one being negative Q. So in this case, for part 2, step 2, what I'm going to do is say that delta V, oh, I shouldn't be writing in red. I'll say that delta V is equal to V final minus V initial, because that's the definition of delta, which is equal to the negative integral of E dot dl, not dA. So this is in fact what we call a path or a line integral. And that specifically means, just like the surface integral meant, that you've got to evaluate the integrand on the surface that you're integrating. Well, on a path or line integral, you have to evaluate the integrand on the path or the line that you're integrating along. And then you also got to either allow the DL to dictate, in other words, to show people which direction I'm going, which direction I'm integrating. Am I integrating in the positive x direction, or am I integrating in the negative x direction? Or am I integrating in such a way that both x and y are increasing, or x is increasing and y is decreasing, or something like that? Those are all different things. Now, you can either do that with your DL vector, or you're going to have to do that with your range of integration. But whichever one you choose, the other one's got to be put in a positive coordinate direction, so that you basically don't get a sort of double negative scenario. So we just be careful of that. That's the main thing. 9 times out of 10, you can't even tell first year calculus students in the first semester or second semester, if you showed them told them to calculate a surface a line integral, they would get it right. That's what I mean by 9 out of 10 times it's not going to matter. They probably get it right anyways, not even realizing that what they were doing. So it's rarely an issue, but it is on occasion an issue. I like to actually work hard to make sure, one, that I understand voltage enough to consistently get a positive quantity for delta V, and two, that my understanding of voltage is so good that I can put it correctly, so that if it comes out wrong or incorrectly or differently, then I'll know that I've made some mathematical error. So in this case, we're actually evaluating an electric field voltage difference due to electric field between RA, which is the outer radius of the inner sphere, and RB, which is the radius of the outer sphere. Okay. Now that inner sphere had a charge of plus Q, and we know for a fact that a positive charge would run away from that towards the outside, in other words, towards increasing R. That must be, in fact, the direction the electric field points, which is what we found when we calculated the electric field. Now, what that means is that the potential energy of the proton, say, decreases as we go from small r to big R. In other words, from R just barely outside the inner sphere to R towards the outer sphere, because the positive charge is actually inclined on its own to move towards the outer one, because that one's actually a negative charge, which is what it likes. Well, it turns out that the electric field pointing that way means the voltage actually decreases that way. So a decreasing voltage would go from a positive charge, say, towards a negative charge. I want an increasing one, so that V final minus V initial is a positive number. So I'm going to go from the outer radius RB to the inner radius RA. So that's what I'm going to try to do with my integral. And I'm going to let the DL do the calculation in terms of which direction we're going. And I'll just use coordinate directions for the range of integration. So I'm going to write down negative integral. Now, since I'm using DL to indicate which direction I'm going, I'm just going to go from small coordinate to big coordinate. So I'm going to go from RA to RB for my range of integration. My electric field is going to be is going to be Q over 4 pi epsilon naught R squared, just like we found earlier, R hat. And then my DL, I'm going to put parentheses around it because I need it to go in the negative R hat direction, and it'll look like subtraction if I don't put a parenthesis around it. So minus DA R hat, that will represent, I said DA, minus dr R hat, that will represent my DL. And notice it does in fact point in the direction I'm going, and the limits of integration, in fact, are going from low coordinate to high coordinate. Now you can see that negative with the other negative cancels out. So we're going to get positive Q over 4 pi epsilon naught integral of R to the negative 2 dr times R hat dot R hat, which make my drunk little owl again, is going to be 1. Okay, and it works actually. It's funny because it works with the X hat, the I hat, the J hat, the K hat, the theta hat. They all look like different moods of a drunk owl. But anyways, let's go on. So this is from RA to RB, and remember RB is actually the bigger number numerically. So the integral of r to the -2 turns out to be 1 divided by -1 times the integral of r to the -1. So I'm going to make this a minus q to take care of division by -1 over 4 pi epsilon naught times r to the -1. So that's 1 over r. So I'm going to evaluate it at the appropriate points, which is first the top one. So that's 1 over rb minus 1 over RA. Now remember, RB is bigger than RA. So if RB were 5 and RA were 4, that would be 1/5 minus 1/4. Well, 1/5 is 0.2 and 1/4 is 0.25. So 0.2 minus 0.25 is going to give you a negative. So you can tell the thing in the brackets there is already negative, and we don't want a negative. So what we're going to do is go ahead and subtract out or change out that negative by flipping the order. So now I'm going to say it's Q over 4 pi epsilon naught. And not only that, I'm going to get a least common denominator. And this least common denominator is going to be RA times RB. And in the order that it was, it would come out to be RA minus RB. But because we flipped the order, it's going to be RB minus RA, which you'll notice is in fact a positive quantity. So that's the actual voltage difference between the two, and that is in fact step 2. Now finally, step 3, we need to use that voltage and the definition of capacitance, which is C is equal to Q over V, to calculate the capacitance of these concentric spheres. So what I'm going to do is I'm going to put a Q up here, and then I'm going to divide it by the Q over 4 pi epsilon naught. And then I'm going to do RB minus RA over RB, put that all in parentheses. You can immediately see that the Q cancels out with the Q, and I am left with 4 pi epsilon naught over, now in this case, all that's left in the bottom is RB minus RA, but on the top, you've got RA times the RB. That's it. That is the actual electric field. Notice it does not have any units of charge or charge density or something like that. It is basically just the geometry of the actual capacitor. So I'm going to say this is equal to the capacitance of the spherical capacitor shells, and I am going to box it off like this. And that's it. We now have completed a typical problem, starting with Gauss's or Coulomb's law and solving for the capacitance. Does anyone have any questions on this one before, for instance, start another one? Okay, remember, you can always go back and watch these videos. Obviously, the downside is they're hour and 20 minutes. The upside is that you can pause them and fast forward them to anywhere you want, and then just watch the part that you need, listen to the sentence I'm saying, or catch what I wrote down on at that particular instant, and then move on. So I definitely recommend doing that. I'm trying to take the magic out of the Gauss's law, because a part of it feels, when you're doing this without understanding, a part of it feels like magic. And if it feels like magic, that means you're probably going to have a difficult times redoing it or doing it yourself. So Now that we've got the Gaussian spheres, concentric spheres capacitor solved, I'm going to do the neat little old-timey antenna wire as yet another example. So let's flip the page. And what we're going to do is we're going to, first off, well, I'll go ahead and draw the situation. So what I have here is a wire that was supposed to be blue, but I've evidently drawn it red. Okay. And then some distance away, I have another wire, and they're supposed to be the same. Obviously, it looks like this one turned out to be a little smaller. And I can't adjust it without doing something crazy. Let's see if I can do it this way. And I can't believe I'm wasting my life away doing this, but anyways, I'm not going to now. Okay, so we're going to pretend those are the same size. And in fact, the radius of those guys, let's take it off of that. The radius of those guys is in fact R. That'll be big R, okay? So that one's R. This one right here is R again. Notice I'm drawing the diameter and telling you what the radius is. Now, in addition to that, it's going to turn out that this distance from the center here to the center here, that's going to be a distance, let's say D. And that's going to be a distance we can assume we know. Now, in reality, like I said, this stuff would have been clad in like some kind of vinyl material like this, and then it would be flat, and then it would be like that around the outside, and that's what it looked like. And of course, this is coming out of the page, so these wires are going infinitely far towards your eyeballs straight out of the page, and infinitely far behind the screen towards whatever the back of the screen is pointed at. That's really what they are. Okay, our job is to calculate the capacitance C, which is defined to be Q over voltage, is equal to question mark. That's what we want. Okay, so we're going to try to figure that out. And in order to do so, I'm going to start off with trying to make sense of the electric field from a cylindrical object by doing a problem that I've already done 1,000 times. Okay, so I am going to right now draw another coordinate system. And in this case, I'm going to draw it right here. And I'm going to draw it right here. And this is only a two-dimensional coordinate system because we don't need more than that because of the cylindrical symmetry. I'm going to call that X, but be advised that X could point straight out at us, and then there'd be a Y there, and everything would be fine. The X could actually point at a 45-degree angle from straight out at us to where it is now, and that would be fine too. So ultimately, what I'm saying is, if I say something points in the positive X direction, that's the same thing as saying it's pointing in the positive cylindrical coordinate R direction. So this is Y here. Now what I'm going to have is a nice little wire. And in this case, the wire is going to be a cylindrical wire of fixed radius. And in fact, the wire itself is going to be infinitely long. I am just, in fact, going to I'm just going to draw a small fraction of it and say that this goes on for infinity this way and goes on for infinity this way. And then to make sure that we don't get confused, when I use my Gaussian surface, I'm going to choose a small part of it. Okay. So in this scenario, I'm going to say, here's my solution. First off, I'm going to make a hypothesis that E is equal to some E of R hat, and this is cylindrical. Okay, because if you thought for a second that the electric field from this charged green wire had a Y component or a Z component, which by the way would be pointing out of the board, out of the screen, or that would be the positive direction, then I can certainly show you a charge on the opposite side of the section where you're saying that would cancel that component out. In other words, the components of the electric field are in fact, let me disabuse you of the idea of using the x-axis, of using the Cartesian coordinate system, because that might be a little more confusing. But what I'm imagining here to make this work is I'm imagining allowing this x-axis and this iPad to stay vertical, and then I could slowly rotate the whole iPad about that y-axis. And everywhere that x points, the x-axis points, is another potential direction that x could point. And therefore, I am saying that that x-axis is really just the equivalent of measuring out the distance r in cylindrical coordinates from the origin along the x-axis. Okay. Which again, if the x-axis wasn't there, it could be from the origin to anywhere, because I'm allowed to rotate this about that y-axis any degree amount I want. So in this case, no, I really got to stick to using cylindrical coordinates. It's just not going to make any sense when I go to start drawing in 3D and stuff. So let's go ahead and now draw our Gaussian surface. And with our Gaussian surface, which I shall draw in red, I'm going to choose, in fact, a Gaussian surface that gives me the behavior I expect, which is that this electric field is going to have cylindrical symmetry. So I'm going to draw a cylinder centered on the z-axis. In other words, its symmetry axis is the z-axis. And this radius right here is going to be just plain r. Okay, now I'm going to say this radius right here, let's say from here to here, this radius r is way, way, way smaller than r. In other words, we're going to talk about thin wire, not worry too much about the details on that. Okay, so with that in mind, I'm going to call this height right here L, and I'm going to assume that this wire is uniformly charged such that lambda, which is Q over L, is equal to a constant. Okay, so by expressing lambda, all I have to do is multiply the capacitance by, if it has lambda in it, multiply that by the length of the wire, and that will give me the total amount of charge enclosed in that particular length of wire. Now, the reason I do this is because you've got some very specific DAs that come from here. So one DA, for instance, might be this guy right here on the top. Well, that DA has to be DA top is equal to some DA. And again, if you had covered cylindrical coordinates, you'd know that's R d theta times dr. But you're not doing double integrals. You don't need to do it. And if you find yourself doing an integral on the left-hand side of Gauss's law, you know you've screwed up. Okay. But it's going to point in the k hat direction, which I think everybody can see, that even if they didn't do the cylindrical coordinates before. And of course, there's going to be a similar dA at the bottom. And in fact, that dA, which I'll call dA sub b, is going to be negative dA k hat. Okay. And then there's going to be, let's imagine a particular radius out, say, and then go over a particular angle theta, and then go up a particular distance r, and then out that same angle theta. And what you'll get is this little rectangular block, and then pointing radially outward from that is dA. And I tend to call this in my class, I imagine this Gaussian surface as if it's a can of soup. That top is obviously the top of the soup can, the bottom's the bottom of the soup can. But this part right here that I'm working on, I call the soup label. So I subscript that just SL, and that's equal to dA. Technically, I should call it dA soup label because it's a different one than the dAs I use for the top and the bottom. In fact, this one is r d theta times dz, if you really wanted to know, but you don't need to, don't worry about it. So this is SL, and it points in the cylindrical coordinate r hat direction. So again, cylindrical coordinate is what we're talking about here. So we can say the Gauss's law, closed integral E dot dA is equal to Q enclosed over epsilon naught, gives me for the left-hand side, this is one of the more tricky ones, the closed integral of, now here's where I need my hypothesis. So let me go ahead and write out my hypothesis. Okay, my hypothesis is that E, the vector field, is going to be equal to E of R hat. I feel like I'd already written that somewhere, but clearly I did not. E of R hat. Maybe I'm just remembering it from. No, that wasn't. Well, yeah, it was because I was using spherical coordinates. So that's what my hypothesis is. So in this case, I'm going to get E of R hat dotted with dA. And this one's going to be K hat, and this is us integrating over the top. And in fact, since I did it this way, I don't actually need the circle of this integral. So let me go ahead and erase that circle, just because, yeah, I'm that guy. And try to make this look like nothing ever had. You saw nothing. Okay. Okay, so that's that. That's just for the top. Now there's going to be plus an integral E of R, oh, excuse me, that vector symbol is not supposed to be up there either. Okay, E of R hat dot dA R hat, and that one's for the soup label. So I'll just subscript that soup label. And then plus, remember this left-hand side of Gauss's law is a closed surface. So I don't have the liberty of not doing the top lid and the bottom lid, because then I could go to the inside and come back out to the outside and claim either one is the inside and the other is the outside. And someone else could do the opposite, because you don't have to actually go through any surfaces to get from one to the other. So you actually have to have the lid on it and the bottom on it. So the other integral is the integral over the bottom, which I'll write as bot. That again is an E of R hat, but in this case, we're dotting it with negative dA K hat. But the most important thing to see with this is the whole reason the dot product is in Gauss's law is because we know that lines of equal potential, I'll get you in a second, Michael, lines of equal potential are perpendicular to the electric field lines, and therefore surfaces on which the electric field is a constant is going to have equal potential lines perpendicular to it. So we want only the components of the electric field that are parallel to those parallel to those dA vectors, so that we get only those components of the electric field. The way you mathematically pick out like components is you use a dot product, whereas if you want to mathematically pick out perpendicular components, you use a cross product, and we'll see that later too. Yes, go ahead, Michael. What's your question?
I was wondering why we write the hypothesis.
Okay, so that's something I added. No, I've never known any instructors to do this, but in some sense, it wasn't making sense to me logically when I tried to think of it from a student standpoint, why we're doing what we're doing. But in reality, what we have to do when we introduce a Gaussian surface is we have to have some reason for choosing a specific Gaussian surface. Like, why do I choose, for instance, a soup can here and a sphere on the sphere? And then, like, for instance, when I did an infinitely large plane, I used a soup can as well, but the parts of the soup can that were important were entirely different. So I said, the best way for me to think about that is I'm making a hypothesis to see if everything pans out by working out the left-hand side. And if I get an electric field times an area, I know it worked out. If it didn't, then I know that my hypothesis it was either correct and Gauss's law can't be used there, or my hypothesis is wrong and I've got to figure out a new one to use Gauss's law in the way we're using it. You don't have to ever write that. That seemed like the most reasonable explanation I could give to my students. So I'm glad you asked, but by all means, you guys let me know if that's not helpful to you, because I only do things to try to help my students understand, not make it worse. So what I'm trying to say with the hypothesis is, hey, there's a certain symmetry of charge here. That symmetry of charge makes me think the electric field has a certain symmetry. And Gauss's law allows me, under certain symmetries, to extract the electric field from the integrand of the left-hand side, but only in those certain symmetries. So in order for me to choose that Gaussian surface, I have an idea what the electric field is shaped like, and I chose to call that a hypothesis. Does that help, Michael?
Yeah.
Okay. Sorry, all my answers are like long. I want to explain them shorter, but I don't want to say anything that seems incorrect or could be misconstrued. So I end up talking longer than I need to, probably. Now, what I was saying about these three parts of the integral, and I left off an important symbol here. We can't have floating dot products with vectors and a scalar. But anyways, the most important part here is the fact that the dot product is a linear operator again. So I can pull the dA in that top integral through the dot, through the left-hand r hat, and I'd get E of r dA and then r hat dot k hat. But hopefully you all know that r hat dotted with k hat. Does anybody know what that's going to be? Zero, because the magnitude of r is 1, the magnitude of k is 1, but the angle between them is 90, and the cosine of 90 is 0. And the same thing happens down here. I get a r hat dot k hat, even though it's a negative k hat, still don't matter. And that's going to be 0. So both of these integrals go to 0. And that's sort of the funny part. When I'm doing a cylinder, the top cap and the bottom cap are the parts that don't matter, and the soup label is the part that matters. But when I'm doing a large, infinite, say, flat surface, I use the exact same shape. Most books call it a Gaussian pill bottle. But in that case, only the top and bottom become relevant. So just keep that in mind as a little reminder of how to work out the integrals. So back to what's left. All I have left now is that electric field evaluated on the soup label of my red Gaussian surface. That soup label has a radius r, therefore E, which is only a function of r, is a constant. So I get E of r times the integral of dA over the soup label. And of course, if you ever took a soup label, which I'm going to draw right here, Okay, that's supposed to be a soup label roughly. And you slid it right here, you laid it out, what you'd find is if this was its height H or L, say, then this would be the height of that. And if this was the radius R, then this distance from here to here would be 2 pi R. So this thing becomes E of R times 2 pi R L. Okay. Does that make sense to everyone? Now I can say the right-hand side of Gauss's law. And this part's pretty easy. The right-hand side, which, like I said, can potentially be the harder part, is in this case, it's just going to be lambda times L over epsilon naught. And that's because the length that we chose to cordon off with our Gaussian surface is just the length L. And as I told you before, lambda is defined such that Q over L equals lambda, and that it's a constant. So all I have to do for any length L is multiply lambda times that length L, and that'll give me the charge. So now I can set left-hand side equal to right-hand side, and that's going to give me E of R times 2 pi RL is equal to lambda L over epsilon naught, which you can see, of course, the L's cancel out. And going back to our hypothesis, that was another reason I put the hypothesis in, is because I was quickly going from this state where I'm getting a magnitude and then writing it out in vector form. And I wanted some structure for students to understand why I could now jump to a vector. And that hypothesis allows that. So here, that's another answer, Michael. So let me now write this as the hypothesis says. The electric field is actually going to be lambda over 2 pi epsilon naught R times R hat. Again, stressing that this R is in fact the R of cylindrical coordinates. Okay, so that is my actual electric field. Now, that's good. We've got the electric field, yay. But guess what? This problem's way bigger than that, because we just finished step 1 and we got 2 other steps. Okay, now what you see is I'm going, and this is, the book does a problem like this, but I'm making this charge right here plus Q, and I'm making this charge right here minus Q. And these are conducting wires, so they'll literally be on the outside edge of those little wires that are diving into the page and coming out of the page infinitely far. Okay, that distance between their centers is a distance d, and remember the distance between their closest points is d minus 2r. Okay, so keep that in mind. Now, what I want to do is calculate the voltage. So that was all step 1. Now, step 2 is me calculating. Oh, that was really bad looking too, wasn't it? Okay. Step 2 is me calculating delta V, which is always V final minus V initial, is equal to the negative integral of E dot DL. Okay, so I've got to calculate the voltage difference from, let's say, one inside edge of the wire to the other inside edge of the wire. Okay, now again, if I put a proton against that left wire, it would not be comfortable. The proton repels like charges, and they're both positive, so the proton doesn't want to be there. And in fact, the proton has a high potential energy there. And because it has a high potential energy, and potential energy and voltage only differ by the charge of the thing that you're testing the area with, the proton being charged means it's going to be high voltage there as well. So I'm going to integrate from the right hand wire to the left hand wire. So I'm going to say this is from R to left. Okay, that's just the way I'm going to integrate in hopes that that'll give me a positive quantity, and therefore I can just divide it and I can check my understanding of voltage and I can check my math and all that good stuff. Okay, so that's what I'm doing for this integral, and it is a path integral, so we got to decide whether DL or the range of integration is going to decide for it. What I am going to do though is I am going to put this in a coordinate system just really quickly by assuming that's my y-axis and by assuming that's my x-axis. And then I can write right in between the electric field. Notice the electric field for the left-hand wire is going to be lambda over 2 pi epsilon naught times x, where x is, well, actually times x minus r, okay, where x is basically the distance. Well, actually, we can ignore the small r because r is going to be really, really small compared to d. So let's say that right from the beginning. D is way, way, way larger than r. That's going to come in handy to make some simplifications and stuff of that sort. So I'm going to put that there. So we can just say that the x coordinates are a pretty good indicator of how far away from the wire you are, because we really should be going from the center anyways. So the electric field, as I said, due to the left-hand wire at any position between the left-hand wire and the right-hand wire is just lambda over 2 pi epsilon naught x, where x is how far away we are. Okay, now the electric field due to the right-hand wire at that same spot, notice it points in the exact same way as the other one does. In other words, it points to the right, but the distance between its center and the position x is d minus x. So our electric fields are going to actually be equal to negative integral of lambda over 2 pi epsilon naught x plus lambda over 2 pi epsilon naught d minus x. And both of those, of course, in this coordinate system that I've drawn up, have a I hat direction, and I'm going to dot them. I've been using the DL to indicate the direction of integration. This time I'm going to use the DL in the positive coordinate direction. So I'm just going to say DL is dx I hat. And then that means I am going to integrate actually from d minus r to d plus r, or excuse me, to r. That's it. So I'm going to integrate from d, when x is d, notice I'm at the center of the other thing. So I'm going to say d minus r to just plain r. So that's basically how I'm going to calculate the voltage. So let's continue on this line. We can see that the lambda over 2 pi epsilon naught and the negative is all going to come out in front. So I'm going to say negative lambda over 2 pi epsilon naught integral d minus r to r, again, r being the little radius of the wire. And what I get is two integrals, basically. You can look at it that way. So I'll draw this as a curly bracket. It's going to be the integral of dx over x plus it's going to be the integral of dx over d minus x. Okay. And again, they're both going from d minus r to r. Okay. Notice the I hats, they just went to I hat dot I hat went to 1. The dx came out in front and all that good stuff. The integral on the left, that should be pretty easy peasy to you guys. You know, it's just a natural log. So I'm going to say negative lambda over 2 pi epsilon naught. This is going to be the natural log. I'll put my curly brackets around it. It's going to be the natural log of r over d minus r. That looks fine. The other one's going to be a little funnier. I'm going to have to, let's let d minus x equal u, then du is equal to negative dx. So, whoa. Yeah, du is equal to negative dx. Okay, so I need a negative up there to change that dx into du. So I'm going to take this plus symbol and get rid of it. And I'm going to call it a minus now. And now I'm going to say the integral of du over u. And again, that goes from x equals d minus r to r. Now, it looks like we only got a couple minutes left in class. So let me finish this up. Now, I'm going to flip the order of these integrations just so I can get rid of one of these negatives because I hate negatives. So this is going to be lambda over 2 pi epsilon naught. I hate negatives just because I dropped them. Okay. Now that one that was negative is now positive, and that's going to be just basically the ln of u. Now the ln of u is going to be the ln of d minus x, basically. So the ln of d minus x when x is r is d minus r. And the ln of d minus x when x is d minus r is d minus d plus r. So d minus d plus r is what happens with that one. And then over here, I get a minus ln of r over d minus r. Close that. Now, remember that multiplication by a logarithm is the same thing as changing that multiplication and making it an exponent on the argument. So I could actually flip over the second r over d minus r. I could flip that over and make it d minus r over r just by changing the positive, and then I'd add those two, and that of course would get rid of the 2 and the 2 pi epsilon naught. So I'd ultimately have just lambda over pi epsilon naught times, now I'm going to have ln of d minus r over r plus ln of d minus r over r. That's 2 times the ln of d minus r over r. I've already taken care of the 2 by canceling out the 2 in the denominator, so I'm not even going to draw that bracket. And all I have now is just a natural log of d minus r over r, like so. And r, of course, is supposed to be so small. You can make all sorts of approximations, but that's what the voltage is. Now, the very last step is calculating what is C. So this is step 3. So C is equal to Q over V. We know Q is going to be, let's say, lambda L. What we have for the V, of course, is this lambda over over pi epsilon naught times the ln. That's lambda over pi epsilon naught times the natural log of d minus r over r, which you can tell now gives us capacitance per unit length. In other words, I divided both sides by L. The lambdas cancel out, and I'm going to get pi epsilon naught. All of that is going to be divided by the natural log of d minus r over r. So that should be the capacitance, barring any careless mistakes I might have made. And that brings us to the end of our presentation of chapter 24. As I told you, I will make some more videos regarding chapter 24. You have, I think, like I said, until like the 13th to take your test 2, which covers chapters 23 and 24. And looking at it now, it looks like I'm shooting towards February 13th to be the day by which you need to finish test 2. That would be, of course, Monday night at 11:59. So I think you've got plenty of time to do that. We already have practice test 1 and 2 available to you guys. I will probably tomorrow or the next day put up practice test 3, and I'll probably go ahead and put up test 2 so y'all can start that as soon as you want. Don't forget, test 1 is due February 8th. That's tomorrow at 11:59 p.m. You don't want to miss that. That normally means in most classes, if you miss a test in college, they're just going to drop you. Obviously, I don't like doing that. So let's just not miss. Okay. Anybody have any questions? I'm going to wait for the last one to leave. Otherwise, you're all free to go. And thank you for coming, everybody. David, are you still there? You have any questions?
Yes, I'm just trying to figure out how to unminimize my screen.
Okay.
Did you get my messages regarding my grades not showing up in Canvas?
Yeah, I'm working on that. I'm not, yours is doing something odd. The other ones aren't. How are you accessing them? Do you go through Canvas or what's going on? How are
Yeah,
you?
I got the Canvas. So if I click any of the assignments, like I can see the grade in the like within the assignment itself. It's just not showing on Canvas.
Uh-huh.
And I'm sure it's related to them, dropping me and then reassigning me to the class. I think it
That
didn't
might,
happen in my other 3 classes, but I think they put me back in the proper way, but then maybe they like did me as a new student or something. But
gotcha. So
the test was the
if
first
you're
thing that
sitting
actually
at your
showed up.
computer in the morning and you got some spare time, tell me exactly after you turn your computer on and open up your browser, how do you go to say homework for chapter 25?
So I'll go to my TCC, then go to Canvas, courses, University Physics 2,
Mm-hmm.
and then either go to modules or grades, either way.
Yeah, that should be doing it right.
Yeah, and then, yeah, like I said, so then I click on any of the assignments and I see the grade inside of the internal thing.
Yeah, so you see the
Like I-
grades in the grade book at MyLab and Mastering. You just don't see the grades at our grade book.
Right.
Okay. Let me
Although
look.
the exam grade showed up today. That's the first one that's actually showed up. The practice test and test 1.
Gotcha. Okay, what I'm doing right now is I'm doing a manual sync. And that actually might be the problem because it's acting like it's never been synced before. So all of this, no, because I saw other, well, maybe I was looking at a different class. I remembered looking and seeing other people were not having the problem, but I'm wondering if I accidentally went to the 241 or 242 day class. You might be able to see it right now if you look in your grade book on canvas. You might see if the effect has already worked or not.
Yep, they all showed up.
It did. Okay. Oh my God.
Awesome.
All this time I've been thinking it was a really big problem. I guess I kept looking at the wrong one, but yeah, it seems that your instructor's an idiot and he forgot to click on the automatic grade sync. Could have swore to have it on, but it was not. So cool.
It probably turned off when they dropped me and re-added me, so that probably wasn't your fault.
Maybe I don't know. Well, I appreciate you extending me the olive branch, but
All right,
anyway,
well, thank you so much.
no problem. Have a good one,
Have a
David.
good night.